work, some of them are not. Let me, oops. Okay, I need to move that off, get that out of there, and get back to here. That is 6. Okay, let me move to 7. Somewhere we, oh, that, what? Did I put video 1? It's the same there as in week 6. Apparently I did. So that video is the same one that is in the next thing. Okay, well, sorry about that. So you can just bounce through that one. Okay, so in this particular part, he starts to talk about moments. So maybe what I'll do is try to fill in the gaps here. Let me try that. Okay, so let's do this. New page, let's just get in here. Draw red. Let me arrange this. So what we're going to do, I'm going to just try to fill in the gaps, so to speak. I guess I can't do it. Okay. So let's say you had a force. Let's say you had like you're trying to tighten a tire bolt right here. So what you decide to do is, and you know, what do they say, righty tighty, lefty loosey? So, oh, let me make sure I'm getting audio here. Yeah, there is audio coming from somewhere, because I can see that changing, but I don't know. I'm not wearing the mic, and I'm being picked up, so I'm not going to worry about where it's coming from. It's got to be in here somewhere. So, okay. So let's say you're trying to tighten this thing. And let's call this, let's say that this little shaft is out here. It's a big piece of metal sitting on your bolt. And this will be X. Oops. And this will be Y. Now, you know the best thing to do is do like that. You know the worst thing to do is to pull it like that. So if you were pulling it out here, you're not going to get this being a torque at all. Now, you can get a torque wrench, but in statics, they want to call it a moment. But the torque and the moment are the same thing. The only distinction I've ever seen that's specific, different, is that for some reason, when the object starts to move, for some reason they call it a torque. It's the same thing. Whether it's moving or not, it's basically a twist or something like that on it. So let's take a specific example here. Let's say this is 3 foot and that's 4 foot. That makes this whole thing 5 foot. Now, if I put a force on here, let's just take a couple of cases. I'm going to use the Alt key to erase this one first. And then I'm going to do something stupid. So here's the stupid person, and they're putting a force on here equaling to, say, 30 pounds in this direction and 40 pounds in that direction. Now, Yeah, it's still the same color. I was just thinking for a minute I had changed colors. No, I had done the eraser. So we have a vector here called r. That's easy enough to come up with. R is 3i and then 4j. Now we know it's 5 foot total, but it's 3 foot out there and 4 foot out there. If you look back, he'll have this written as a moment. So what I'm going to do now, you can go into the textbook and you can see this, but also instead of me trying to find the textbook, I'm just going to go do it. And I'll say it's R cross F. Now I'll give you a particular case. Well, let's do this one out and then we'll go back and look at it. So if I look at that in a matrix form, because I like to see them like this. The reason I like to see them like this is because I can see everything all in one area. And it's pretty easy to multiply it out and everything. Let me make sure I'm streaming. Did I hit the streaming button? Well, apparently I did. For some reason I thought I didn't. Usually I get a notification on my phone that tells me that I did that. Let me see, is there something wrong? Oh, there I am. Apparently I did. Oh, there I am. For some reason I thought I didn't. Okay, there we go. So I'm there, there's audio. I don't know where the microphone is. It doesn't really matter. So if I look at the R, it's 3, 4, and nothing. And then the F is 30, 40, and nothing. Did I list that right? I guess I did. So then I look at I. Now here's what's so funny about this. If you look at I, what you're supposed to do is you're supposed to eliminate this and that. And then that gives you the little matrix to deal with. Minus J. If you do J, you're supposed to eliminate this one and that one. The fact that this sits right there means that the I component, the Y component and the X component are non-existent. Does that make sense? Ooh, why did it not go away? There we go. So that means the only thing I get is the K component. And 3, 4, 30, 40. So, can I do an arrow down last time? Oh, it does work. So I look at this thing, the only moment I get, apparently it takes away my ink pen. The moment just becomes the K component, 3, 4, 30, 40. Well, if I take this one, I get 120. Take that one, I get 120. But I'm supposed to put a minus sign here because I'm coming backwards, so I get a moment equaling to 0. So this is what a not so brilliant person might do, who doesn't know. I wish this was a touch screen. I don't know. What happens if I push that button? Nothing happens. What if I do? Oh, your next touch will be a right click. What the heck is that? Okay, that doesn't work very good. Okay. Go away, go away, go away. All right. So let's go back and let's say now that we have a person who might not be so bad. So let's say he decides to put a little bit more in this direction. So instead of 40, we're going to go back and say 60. How about 60? So let's say, and I'll try to draw this, try to do a decent job of drawing this. So now I'm going to put a 60. So that means it's sort of like this. So now this is the force vector. And I'm using the blue just so I can go through there and sort of change things. So what I'm going to do is I'm going to scratch out, put a 6. So everywhere I see a 40, I put a 60. And then apparently, this is not a touch screen, so the mouse rolling key. Yeah, there you go. And so now I have a 60. I have a 60. Doesn't matter here. This doesn't matter. This doesn't matter. And so I get 3 times that. So I get 180. So now I get 180 minus 120. It should be 60. Let's say everything was foot and was pounds. So let's say you get 60 foot-pounds. Now, let's look at this in an interesting way. Let's see if we can decipher this somewhat. If I were to look at it like so, there's a component going this way, and there's a component going out there. Now, I guess there's really kind of no point to actually this exercise. I was going to find this component right here, but there's no real point to that necessarily, because it really doesn't show anything. The key is we come down to this simple equation for any moment applied along anywhere, and that's all there is to it. The complexity comes into how many moments you have, how are they applied? Are they applied with a rope? Are they applied with a string, or whatever? So let's take a look at some cases in the homework where I think these will come out. Okay. So what we'll do, we'll roll. I think I was looking at 7 a minute ago. Determine the moment. That's too easy. Let's go. Oh, here we go. 2 men are pulling. This is a good one. There's 2 guys are pulling here with this. Determine the moment of each force about point A, which is that little spot right down there. Okay, take that. So I really don't need, oh yeah, I guess I do need some information from the thing. Okay. Here's what I'm going to do. I'm going to add a new page. I'm just going to drop it like right up there. Then I guess I am going to need some of that information. This thing, I mean. Okay. 2 guys are pulling. I got to know who's pulling with what force. Otherwise, I'm going to mess up. So let's put that right there. Oops, not right there. How do I do that now? I've never had that happen. Lasso? Do I select with a lasso? Oh, guess I do. Okay. So now I need to get back a pen. Okay. So we know this. We know that the total moment about A is going to be, and I'll call these forces, well, I guess they're called F and P. R2F cross F plus the R that's drawn to P crossed with the P. The next key here is I need to know all 4 of these, the R and the P. I'm going to do the easiest thing first. If I drew an R that went from A, maybe I should A to F and A to P. From A to F, man, that is so simple, especially if I make that the X and I make that Y. That vector just goes straight up 12, J. Man, that was easy. R that goes from A to P, I think 12 and 6 is 18. So those were really, really simple. They're so simple that I'm going to try to move them out of the way. Let's see. Go from here. It's right there. Now I'm going to start working on the F. I'll just start there with F. We got to switch back to my pen. I'm going to go to red. So I got a component going this way in my F, and I got a component going that way. So I'm going to break it down. So I'm looking at F first. He tells me F is 80 pounds. So I'm going to go ahead and take that 80 pounds. How much is going in the X? Well, there's 4/5 of it going to the right. And going down, 80 times 3/5 of it going down. All right. The other one has a 45 degrees, so let me start pulling out the eraser now. So now, let's go ahead and do the P. Oop, that's a P. This is a P right there. He says that's 50 pounds. Now, if this is the case and this is going down and to the left, this is 45 and this is 45, then I don't even think about the sine and cosine, because I start looking at this and saying, well, this is 50 over square root of 2, and this one has to be the same thing. Now, if you square that and then add it to that square and take the square root, you get back 50. Because that, and the reason that is cosine of 45 equals the sine of 45, and we love 45, and it's 1 over square root of 2. And so when I see a 45, I'm happy. I don't even have to think of trig. So, okay. Ooh, that is not 8. Hang on. Plus, I need to move this to the right a little bit, because I got to put a minus sign in front of that. The reason I got to put a minus sign is it's running backwards. 50 over square root of 2. And guess what? The other one's running down. 50 over square root of 2. J. So I got all the ingredients. Got this. Got this one. And I got my two R's there. So I'm pretty good to go. I just got to go down and do the math. Now, let me get rid of some of this garbage here just because, you know. Okay, so what I'm going to do is I'm going to list them out. My moment total, I'm going to do this one first, of course. And I'm going to list them exactly like that. And I'm going to realize in all of these, I only get a K component. But myself, I like to list all three. The reason I like to list all three is because we're in 2D right now with these two guys here. But in a minute, maybe not a minute, maybe next time, we'll be in 3D. So I don't want to do something that's not going to cover itself in 3D. So I want to make sure I'm doing, you know, what I need to do. So first, R, A, F. Man, that's easy. So I'm grabbing RAF, sticking it right there. Next, I got to get the F, which is this thing, and I got to stick it right there. Oh, geez, that's kind of, I'm going to have to write really tiny. 80 4/5 and minus 80 3/5 and then 0. Then I'm going to go over here and I'm going to go ahead and do the next one, which is RAP. Goes right here. That's pretty easy. REP is 18. Did I do those right? 18 REP, yes. Okay, I think so. If I mess up and I'm not doing them right, let me know. 50 over square root of 2 with a minus, and then a minus 50 over square root of 2 there. Then I'm going to roll down, and I'm going to recognize right off that I am only going to have a k component here. I'm only going to have a k component here. Matter of fact, I'll always only have one. So I'm just going to stick. Now, let me rephrase that. Okay, I have a k component only because I only have a two-dimensional thing. When we get 3 dimensions, it's possible to have a moment that has an x, y, and a z. So just be aware of that. Hang on. I'm still going. So, all right. So I'm going to only have a k. So believe it or not, on a k, I only have this times that. That's pretty easy. That was an easy one there. And then I have minus this times that. That gets stuck right here. So you know what I'm going to do? I'm going to put a minus 12 times 4/5 times 80. That's all I got out of this one. And interestingly enough, I got something similar here, since this is the way, since basically the vector goes straight up, both of them are going straight up. That means the y component, if you look at this, the y component of either one of those forces do not participate. Let me highlight that. If you look at that, this and this, it does not matter what value that load is. This could be 1,000,000. This value could be 1,000,000. This could be 1,000,000. Doesn't matter, because whatever that is, it's going straight down. It's not producing a moment there. So those are inert, so to speak, if you want to call them that way. Alt, blue. Now, so I can write that and say it's 0, or just completely ignore it, and then grab this one and stick down here. Now, this one, since it's going and it's multiplying across there, it's negative, but it has a negative number, so I end up with 18 times 50, is that right? Yeah. Over square root of 2. For some reason, yeah, okay. Maybe that looks okay. Well, I guess I could multiply that out, or at this particular point, let's decipher it before we go any further. Here's how I'm going to decipher it. I think I can fit this on one screen. And next, I'm going to use the eraser to clean up this drawing here a little bit. And then I'll use red there. So let's do this. Let's say this component right here, okay, F is 80. So this component, there is a component going that way. We already determined that produces no moment. So we're focused only in this one, which is 80 times 4/5. Let's scroll up with the mouse scrolling wheel, and let's look at the component that goes this way. Now, it turns out these two components are the same because it's 45 degrees, but this one produces no moment. This one, on the other hand, does. Now, if I multiply the distance times this, think to yourself, you're out in the car, your tire's flat, you take a tire changing tool. Here's your tire. That's one of the bolts, and in this particular case, you're kind of loosening it. then you're probably wanting to pull perfectly perpendicular, because if you start pulling this way, you're just wasting your effort. And what you're doing is you're doing 90 degrees to that, and then your torque there on your torque wrench should measure that times that force, foot-pounds. So with that in mind, we can approach this that same way and say to ourselves, okay, this one is producing a torque this way about here, which is actually 12 times 80 times 4/5. That's the length out to the force, and then the perpendicular force out to the right in this case. Now, I should have color-coded this. So this one is producing a torque that way. I say a torque, but I'm only saying it because I'm referencing, but technically in this course it's supposed to be a moment. Who cares? 50 square root of 2, this time times 18. So if you look at it and you logically work your way through it, that's what you see. Now, here's what happens if you're looking at this in a coordinate sense. Here's x, here's y. Take x, point your fingers out in x and roll them towards y in this way, and your thumb will point to you, meaning that is a positive moment. So technically, this one is a positive moment, and that one's a negative moment. So let's scroll down here and see if we match up. And in fact, I think we're pretty matchy here. Well, let's do this. Okay, so here's this one. In fact, it is negative. And then here's this one. Sorry, this one is positive. So in fact, your visual perception there and the mathematics match out just to be fine. They're both the same thing. So with that, but the thing is, okay, the reason I start here with these is because this always works. If there's some sort of odd or bizarre geometry, then I just break it down to a simple thought. What did he want to know the moment about? Here's what I mean. He says, determine the moment of each force about A. Then draw a vector from A to the point of the application of the load. I don't care where that load is. Draw that vector. And then what you do is you cross it. It's that simple. And then if you have two of them, like in this one, you add them both together. So it's that simple. Now, let's do something. Well, no, I don't necessarily want. Well, maybe I will do it. But we've already done this one. Let me come up with a. What time is it? Yeah, is it good enough to come up with another? I'll make up another picture and we'll do something interesting there. So does this all make sense? I'm going to come up with another picture. My pictures aren't going to be as good because I can't draw those little guys and everything. But I'm going to get back to let's go to a black thing now. Let's see, full screen. Let's do something really bizarre here. It's not necessarily that bizarre. We're going to draw a vector out here, and then somebody is pulling this to the right. So here's your force. It's going to be equal, and this always is going to be x and y. Force is going to be equal to, just make up 10 pounds in the x direction. Now, I'm going to come up with the vector that gets us there. Okay, well, That vector 30 I plus, I'm just going to make it 40J. So what is the moment of this force about this point A? So let's just find this out. Now there's something that's going to be interesting. I don't know why I'm writing them backwards. So there's your moment. So I, J, K, the R, 30, 40, nothing, 10, nothing, and nothing. Now, what we're going to stare at is we're going to stare at something interesting. That interesting thing we're going to stare at. Hang on. Do the Alt, yellow, and that is this. How does this number affect that moment? So if we carry this out, first thing, we only have a K component. In this particular case, that's all we've got, because this will, these two zeros, the fact that it's in a plane means it's going to clobber the rest. So I got a 30, you got a 40, you got a 10, you got a 0. And then I guess I'll just write my K. So I got that times that, 0, minus that times that, minus 400? I think it is. Okay, the first thing I see is, appears to me, because this is 0, now, this is, what I'm trying to do is show like a concept here, is that this 30 means nothing. It's gone. So what that means, let me go back, I'll go to blue, that if I drew that vector right here, and this is F is equal to 10I, then this R, the R to that would be R is equal to, this time, it'd be just 40J. Or I could draw it back here. Or I could draw it out here. Or I could draw it out here. Fact of the matter is, nothing that you do with this R that sits right here, no value there that you put, is going to affect that moment. So the fact that you can take a line, okay, how do I do that in here? I know how to do it at the house. They may not have a ruler here. I don't see one. But anyway, okay. So if they don't have a ruler, here's what I'll do. I'll use a little green. So if I take this line and I'll look along this, this is what's called line of transmissibility. In other words, I could translate that force anywhere along that line and I get the same moment. Well, so why don't I just translate it back to here? And if I do, I can look at this distance, that distance, which in this case, what is that, 40, and multiply 40 times 10, and I got it. Now, I can do something really bizarre, but it will come up with the same thing. And what I mean by bizarre is this. Here, let me show you what I mean by bizarre. It's not, we could do the math on this if you really feel like you want to. But let me set a different situation, and you'll find something interesting. Where did my mouse go? Oh, here we go. Why is it not working this time? Well, okay, I'll just draw it. Maybe I can figure out how to get it to work here. So this time I'm going to draw it. Here's my R. This time, my force is like that. Oh, there we go. Okay, line of transmissibility means you can just take that and draw a line. And I could go further, but it'll go into the other problem. So anywhere along that. Now, what I can do, and this is what people generally do here, is they'll say, okay, you got this. Let me change back to that color. You've got this vector r here, right? But if you found this distance right here and move that f to right there, then it'll be nothing more than that distance times f. Now, if you want me to prove this, we can do something interesting, meaning we can take the problem above and rotate it. And we can do that in MATLAB, and I can show you that no matter how much you rotate it, that this always becomes the same thing. If you can find the perpendicular distance from that line of transmissibility, take a perpendicular line until you drop right through here and find that distance and multiply times the magnitude of that force, that will give you your moment. That's pretty handy sometimes. Let me give you a case in point that's pretty handy if I can get that. Wait a minute. The mouse is acting weird. Okay, if I go up. Oh, by the way, I didn't finish the problem, but you can finish it and get that. So here's a case in point. So if you want to know the moment at where? About point B of each of the, oh, that's funny. I thought it would ask about point A. Okay, well, all right. Well, all right, here. I'll go ahead and copy it and think about this. Okay, copy the clipboard. Let's just drop it right there. If you're wanting to know the moment about B, which that's okay, you just look across here, go to that, find that distance. The perpendicular part of that load is 4/5 of 500. So I think that's 400. And then that's distance is 5. This one you just scoot on out to 5, and that's 11 times that. And I don't know, I'm guessing that he may tell you each one of these, I don't know. Then you have you could draw a line to right here. Problem is, this vector, this F3, is broken to a component that goes that way, doesn't produce a moment, and then a part that goes that way. And so whatever that is, which that is 30 degrees, so that's going to be half of that. That's going to be 80. And then half that's making that 40. So you get this force twisting this way, this force twisting that way, and that force twisting that way. They're all twisting the same way, apparently. So now, if you decided you wanted to really just wanted to be very inefficient and work super extra hard, which I don't vote for that, but let's look at this one. I'm going to zoom way in on this thing. It may become pixelated. But let's say you decided to do something. You looked at this one and you decided, I'm going to look at this 160, and I would really like to work hard and waste a lot of time. How can you do that? Well, here's what you could do. You could find the line of action there. You could find this distance, and then you multiply times 160. What you're going to find is you're going to have to use this 30 degrees. I guess I'd have to zoom it in even more. And probably have to use one of those thinner pencils here. Let's try that. I'll use the thin one. So if I were to draw that triangle, that's gonna be the distance, right? This is a half, that's 30, so that's gonna have to be 0.25. So 0.25 times the full load, 160. What's 1/4 of 160? Set. Okay, so 160 cut in half is 80. Cut in half again, that's 40. Now, if I did this, it said, hey, wait a minute. This force is, okay, because that's what sine of 30 is equal to a half. That's how I got that half. So that sine of 30 times the 160 gives you this being 80. Now the moment arm is a half. So a half times 80 gives you back 40 again. So either way you do this, you're going to get the same thing. You could transmit this force back and find that distance, meaning that little triangle right there. It won't zoom in anymore, but because the reason being is because that is perpendicular, or you could do it the other way. They both work out the same way. At times, it's easier to transmit that force. At other times, it's easier to take the component. It just depends on the geometry and the situation. Hey, they're leaving. We should leave too. Uh-oh, am I still streaming? I hope I am. Oh boy. I don't want to leave anybody in the dark. Let's see. Hey, they're leaving. Oh, there we go.